Hello everyone, welcome to our webinar about energy harvesting for long-term IoT deployments. My name is Alex Raimondi, I'm the Director of Embedded at Miromico here in Switzerland. I joined the company in 2002 and I have about 23 years of experience with hardware and firmware development. Within Miromico, we offer electronic product development with a strong focus on IoT devices, wireless, low power, long range devices. Myself, I have a master degrees in electrical engineering and information technology from ETH in Zurich. Webinar, we will record everything and we'll put it online in the beginning of next week. All the materials will be available and will be shared on our website, including slides and link to the presented components and also the contact for the presenters. During the webinar, you can always type questions at any time into the Q&A section. And please remember to indicate the speaker you want to address with your question. At the end, we will have a Q&A session and we will answer all the questions as far as we can. What is energy harvesting about? So currently in IoT, a lot of devices are deployed using batteries, which will create some additional costs in running a system for battery changing or even environmental cases where we have to replace batteries and recycle them and replace it within an installation. So energy harvesting is a upcoming and quite fast growing part of replacing batteries with energy sources created from, for example, light or movement or heat. And within this webinar, we have 3 presentations which introduce technology starting from how we create the energy with the transducers, so for example, photovoltaic cells. And the second one is convert those kind of electricity into some usable currents and voltages. And in the end, we have application circuits which in the end are capable of running on very low energy and making use of all those energy harvesting. In terms of presenters, we have Jonas from Epishine. He will give a good introduction on their key technology, solar panels. Then we have Luc from EPS, who is in a company that creates energy harvesting solutions, and Andres from Miromico, who is into application development for energy harvesting IoT devices. As a first presenter, I would like to introduce Jonas. Jonas is co-founder and CTO of Epishine. Before Epishine, he was working on organic cells in the University of Linköping, and he's co-author of Nature Energy publication on high-performing organic cells for energy harvesting. Jonas holds an engineering Master of Science with Applied Physics and a PhD with Organic Electronics from Linköping University. Now, Jonas, the word is on you.
Yes, thank you very much, Alexander, for that kind introduction. Let's see if I can share my screen now. And you can see it?
Yes, now Jonas, you're ready.
Now you're on. Fantastic. So yes, thank you very much for that kind introduction. So I'll give 15 minutes here focused on light energy harvesting and organic photovoltaics. So I'll start with a brief presentation of Epishine and then go over some introduction to light energy harvesting and then continue with more information about organic solar cells and the technology developed by Epishine. So very briefly, Epishine is a startup company spun out of Linköping University. established 2016 with headquarters and production facilities in Linköping, Sweden. We are now 20 employees and focus is development and manufacturing of organic solar cells for light energy harvesting, or rather organic light cells, because we use them for artificial light sources indoors. So as you mentioned before, there is a number of transducer technologies where we can convert forms of energy into electrical energy to replace batteries, such as thermal, vibrational, radio frequency, and light energy harvesting. For indoor application, especially in the built environment, the only available source with relative energy is light energy harvesting. So this is now what we will focus on. So the intensity of light is directly proportional then to the power we can extract. And indoors, we measure the light intensity in lux. This is a unit derived from the human eye, and relative values are for direct sunlight. We are at 100,000 lux. Typical indoor light intensities are somewhere between 50 and 1,000 lux. So typical application that we look on is this, and mainly focused on around 500. I also have some images here to give a feeling for the distribution of light indoors. This is images from the company Velux, and to the left you see a generation of indoor environment, and to the right you see the distribution of the light intensity, and typically you can see that the walls are around 200 lux in this image, so intermediate. On the floor in the center of the room you have the highest light intensity, and up closer to the roof the light intensity is lower. So typically you need to adapt to where the light is and what the light intensity is when you want to use light energy harvesting. Also indoors, the spectrum is a little bit different compared to solar light, because solar light contains a lot of infrared radiation. And classically, also the indoor illumination has been dominated by incandescent light bulbs. However, they are now banned in Europe and out also for many places otherwise. So the light, artificial light that we use for indoor illumination is now contained in the visible part of the spectra between 400 and 700 nanometer, dominated by fluorescent and LED illumination. So to make a good energy harvester indoors, we want to absorb the visible part of the spectrum. Also, a brief introduction now to organic solar cells, where sort of the main driving points is scalable roll-to-roll production, which can enable then a low cost and also a very short energy payback time, as the material consumption is very low. Other unique properties are flexibility, lightweight. They can be made semi-transparent, and it's also possible to tune the color of this type of solar cells. So the OPV structure you see here an image of, it's a stacked sandwich basically, where we start with a PET sheet. In the bottom you have the TC, which is a transparent conductor. On top of this you see something called ETL and HTL. These are layer sort of membranes to make sure that the current is guided the correct direction through the cell. And then you also have the active layer, which is the layer that absorbs the light and converts the light energy into electrical energy. This layer is typically 1 or a few hundred nanometers thick, which then compared to a human hair is about 1,000. So it's very thin layers. This layer in turn is then composed of 2 different molecules. Classically has been a fullerene, buckyball as you see up here, and a polymer that could look something like the one down to the right where you see the monomer. These ones we then blend to form the active layer. This is the unique thing with organic solar cells. So we also now have a quite recent publication together with colleagues at Linköping University and also at Academy of Science in China, where we have worked with novel materials. So we replaced this fullerene material then with new materials. And as you see to the right, the quantum efficiency or the current generation is very efficient then in the visible part of the spectrum where the light available is. What is also very important now is that we generate a high voltage, because the amount of light absorbed is proportional to the current the solar cell can generate, and then current times voltage is power. So we would also like a high voltage. And as you see, this material under solar illumination has then a voltage of more than 1.24 volts, which makes it a very good candidate then for light energy harvesting. So we also evaluated this material, and then under artificial LED illumination, we could actually achieve a power conversion efficiency of close to 25%. Now note that this is not the power conversion efficiency we would have under one sun, but this is under a LED light source. And we were very happy with this. And as a sort of reference then, so at 500 lux illumination, as we discussed before, typical office illumination, we then can generate with this device 37 microwatts per square centimeter of solar cell area. And if we then compare this to other technologies, classical amorphous silicon, which used to dominate for calculators, the power density ballpark for this technology is somewhere between 10 and 17 microwatts per square centimeter. Gallium arsenide, which is the most efficient solar cell single layer technology, are somewhere around 40 microwatts per square centimeter. And you see that this material actually now can match the performance of gallium arsenide, but then with advantage that it can be produced as a lot lower cost and without the toxic features then of gallium arsenide. Also, we have then a roll-to-roll production developed at Epishine, where we now have where we're working then with this fullerene material still, and then we can reach a power density of close to 20 microwatts per square centimeter. And then, of course, our R&D programs are now focused on achieving higher performance for the future. What is then important when it comes to indoor photovoltaics is that you have a very high parallel resistance. So if you have shunts in your device, this will impact performance severely, negatively. So to the left, you see a typical IV curve then for a solar cell, where you see in red the light curve, and this you would like to look as much as an L as possible, because then you can extract the maximum power. And then above this in dark, you see the dark curve, and this is flat and nice as it should be. But then if we take exactly this solar cell and put it under low light illumination, and we focus now on the dark curve, you see that this curve is actually not as flat, but there is a bit of shunting in this device, and this also impacts then the power curve, the blue one you see under low light illumination, and this looks very much not like a L, and this also means that we lose a lot of power. So this is now a critical issue. Shunt illumination is critical to have a high yield and good indoor performance for indoor photovoltaics. And I also remind you then of the structure of organic solar cell. We remember that the active layer is about 100 nanometers, so it's extremely thin layers. And the classical way to manufacture organic solar cells is that you take a PET foil and then you coat in a roll-to-roll process layer by layer by layer. And then with these thin layers, there is a very high risk that you get small micro pinholes that de-wet the surface. And if you do, then when you coat your top electrode, you may get contact between the top and bottom electrode, and then you get shunts in your device. And here is the core technology of Epishine, and the technology that we have developed. So instead of coating all layers on one PET sheet, we coat half the solar cell on one sheet, the other half on another, and then we use heat and pressure to laminate these ones together. And this way, we have a very efficient way to avoid shunts and thereby generate high performance indoor light energy harvesting devices, also with a very high yield. We have a production facility, as I said, in Linköping, where we use printing, coating technologies for the organic layers, and then we also have conversion process to make this foil into the products that you see here examples of to the right, and we also have a tester there, so we can make sure that we test everything before we ship it out. What we then can do with this is that we can integrate it in different products. Here we have just some examples of switch buttons with Epishine light energy harvesting devices integrated. Could also be electronic shelf labels like here, or a lot of sensors, etc. So for applications, there are numerous things where we can then either extend or replace batteries. So typically, for the first now LEH3 series that we can offer, the basic thing then to do to consider whether this is useful or not is to make a first approximation of the power density, and this you do by basically measuring the light intensity. So as an example, at 500 lux, as I said, we can generate close to 20 microwatt per square centimeter active area then of this device. And the power generation scales linear with area. So if you take 10 square centimeter, you get 200 microwatt, etc. And the power scales almost linear also with light intensity in the range between 50 and 1000 lux, typical indoor illumination. So as a first approximation, if you have 50 lux, you could count on 2 microwatts per square centimeter or just below then. To see how much power is available. And then I think this discussion will also continue with look later on to design circuits for how to utilize then the energy generated by light energy harvesting. Oh, thank you very much for your time and listening to my crash course here in light energy harvesting and organic solar cells developed by Epishine. For technical questions, I would be very happy to answer them. And if you're interested in orders, evaluation modules, evaluation kits, data sheets, etc., so please contact my colleague Jonas Palmer, who is responsible for sales at Epishine. Thank you very much.
Thank you, Jonas, for the interesting introduction into solar panels. Now I would like to hand over the word to Luc, who is working at EP's Senior Sales Director for the EMEA region. He has 24 years of experience in working in the semiconductor industry. He was a former ASIC designer and now is working with EPs and is which is providing solutions for energy harvesting in chip scales. Luc, please take over.
Hi, Alex. Yeah, thanks for this nice introduction. Hello, everyone. Good evening, good morning, wherever you are. So let me just share with you also some updates about the EPs. And you should be able to see that on the screen. Is that correct?
Yes.
Yes. Okay. Thanks. All right. So let me shoot the presentation. So first of all, let me give you a quick glance of EPs. So first, EP stands for the electronic portable energy autonomous systems. We are a bit older than Epishine. We were founded in 2014. We are a fabless semiconductor company. We are focusing on designing integrated circuits, and basically we are also focusing on ultra low power design or applications. Such applications are, for instance, the retail market segments, agriculture, automotive, or also industry 4.0. And we are really focusing on the energy harvesting type of applications. And we also have some products related to computer vision and also to edge computing with an ultra low power MCU. But today we will be focusing only on the energy harvesting. We have about 25 employees in 3 different locations. The headquarters is in Belgium, close to Brussels. We have a design center we also have a design center in Switzerland, and just recently we opened an office in the US on the west coast. Okay. So really our mission is, like Alex, you mentioned, is also to extend the autonomy of some ultra low power devices. This is really our main focus, and basically there are 2 angles to do that. The first one is you need to harvest more using the ambient energy which is available. The second angle is also to consume less, and that's why we have developed some special techniques to do some ultra low power designs. And then finally, our goal is also to ease our customer's life and to provide also some complete system solutions, including the software, including some modules and so forth. Okay. But looking at the energy harvesting for low power, basically what we have at EPs is basically we have a power management IC. That's the one that you see on the left, which will manage the energy from the harvester cell, like from the Epishine PV cell, for instance. That will charge a supercap or rechargeable battery. And also we may have an MCU which will compute the data that you have measured, that you have sensed. And basically this is what we call this edge device, where you have those different components with the different sensors, temperature, gas, humidity, whatsoever. The processing unit, which would be the ultra low power MCU that EPs is also developing. Our power management IC, which is currently available. And most of the IoT devices are wirelessly connected, so you need at some point also a radio chip, like a Bluetooth Low Energy, LoRa, Sigfox, narrowband IoT, or whatever. Okay, so this is how our products are fitting in the scope of energy harvesting. But looking at the harvest more, basically at EPs, we are supporting, in fact, 4 kinds of types of energy sources. The first one, and this is what we see on the market, is really the photovoltaic. And thanks to the solutions of Epishine, and we are collaborating already with them on several cases. We also have a dedicated chip for the thermal, where you take the benefit of a temperature difference to generate some voltages. And then we have the AC sources, which is divided into 2 parts: the vibration, which can be piezo, MEMS, whatsoever. And then the other part, which is, we call it high frequency or RF, radio frequency, where you can use also frequencies like 868 megahertz, 2.4 gigahertz, whatever. Okay, so those are the different kinds of energies that we are supporting, and we have a dedicated chip for each energy source. Those are some examples of customers or applications that we worked with. We are, as I mentioned earlier, we are in the agricultural business with some cattle tracking system using PV cells in this case. Asset tracking, asset monitoring, predictive maintenance is a big trend that we see so far. And there was an example of Epishine for the electronic shelf label, and this is what we have with the ESL market, which is a high volume for us. Then you have consume less, and this is the MCU that I mentioned earlier. We will have an MCU being developed to be released to our customers towards the end of this year or early first quarter to 2021, which will be Cortex M0 based. Okay, and we have different families targeting high computing, ultra low power, or sensing type of device. But focusing on the energy harvesting itself, basically, you know, the IoT devices. This is not something new to you. IoT devices are everywhere to collect some data, to do some measurements, to do some tracking. Those are using batteries, and they need replacement, which implies some additional cost for maintenance, which can be troublesome somehow. So that's why energy harvesting, and this is what we see on the market, energy harvesting is getting a lot of attraction there. And this is one of the solutions to address this. You may add features because you have more power, so you can add some functionalities. You can reduce the size of your storage element if needed. You can extend the lifetime of your existing battery. And as I said, you remove the maintenance cost because you have a system which is completely autonomous. Those are the different market segments where you see already in production energy harvesting. Agriculture, I mentioned. One big focus is also the Industry 4.0 in warehouse, for instance. Healthcare is a big trend. and also wellness. With, for instance, we are discussing, or we are working with some sport watch companies, for instance. But why do you need energy harvesting? Which would be a good question to answer. Basically, you need to have a harvester, a solution from Epishine. You need to extract this, and you need to store it at some point. Okay, and basically those are the 4 different energy sources that we do support: the PV cell, the antenna for ERF, TEG for thermal generator, where you take benefit of temperature difference, and then vibration or mechanical generator. Okay. But why would you require an AEM, Ambient Energy Manager? This is the product family chip that we are developing. You need to extract the maximum power from the harvester, get the best efficiency, and you need also to be able to start from a very low voltage, and this is what the concept of what we call the start, and I will come back to this later on. Okay. Based on that, using our AEM chip, then you can either store this energy into a rechargeable battery or a supercap, or you can directly supply your hardware if needed. So why do you need to have this device in between the harvester and the storage element, for instance? As I said, you need to extract the maximum power from the harvester, and we have some mechanism to extract what we call the MPPT, the maximum power tracking device. You need to start from a low voltage, and this is what we call cold start, and our devices are able to start from 380 millivolts and as low as 3 microwatts, okay, which is a key feature. But you need also to protect your storage element against overcharge or over discharge, okay. And of course, you can also supply directly your device with the voltages that our AEM family is managing. Okay, those are the main reasons why you will need a kind of power management IC. The other feature also is that it's not software configurable; everything is hardware configurable, so it's easy in terms of integration, which is a key feature. And as a summary of the performance of the device, in terms of leakage, it's pretty low. It's only 400 nanoamps there. The cold start I mentioned earlier, 3 microwatts, 380 millivolts to start with, this that we need from the PV cell. The other thing also which is important I mentioned is MPP tracking feature to extract the maximum power from the harvested cell and get the maximum efficiency. And then you need to protect your storage element against overcharge, over discharge. Sorry. And also, we have a capability to deliver 2 kinds of output voltage supplies to your device: a high voltage, let's say high voltage 2.5, 3.3 volts, or low voltage 1.2, 1.8 volts, for instance. Both can be combined, or you can choose only one of them if needed. Okay. You may also need to have what we call a primary battery or backup battery in case, for instance, the PV cell is not performing because you have some cloud, not enough light, or not enough sun. Or you may also use a primary battery in case the rechargeable battery is completely empty, for instance. Okay, so you have this option which is available. You can connect a coin cell battery, CR2032, for instance. Okay. So those again are the different products that we have in the pipe. For the photovoltaic, it's really the 10941, which is the key product for you to consider. Devices are available in the QFN package, but we of course we do have also evaluation kits for our customers, and then where you need just to select the PV cell that you need, for instance, Epishine, and you need also to select the type of storage element that you will need, a supercap or rechargeable battery. Okay. So what makes the AEM family unique? We have a very low cold start, 3 microwatts. In terms of input voltage, I didn't mention that, but the input voltage is we accept 5 volts up to 110 milliamps from the harvester cell. We need 380 millivolts only for the cold start. Very low quiescent current, leakage current. We call it global, so it takes into account all the leakage from the boost structure, from the boost circuitry, from the buck, from the LDOs. Actually, on the right, you have a very simple block diagram of our device. You need only 7 passive components to connect on your final PCB. Those are 2 inductors and 5 capacitors, and basically everything fits in less than 1 square centimeter. Okay. As I mentioned, you can generate 2 output voltages: high voltage, low voltage, 80 milliamps for the high voltage, 20 milliamps for the low voltage. It's easy in terms of integration. It's only hardware, no software to be developed. Okay. In some particular cases, we may also do some customization for if we have the right return investment ROI on this. Okay. And maybe one of the final slides is just more details about this the out chip dedicated to the PV cell, the 10941. As I mentioned earlier, so we need only 7 passive devices to be connected. It's available in high volume production. We have many applications using this device. We are in continuous development, and basically we'll have towards the end of this year actually a smaller form factor version of the device, which will be in a 2x2 millimeter as a WCSP, wafer level chip scale package. One of the applications that we are targeting for this one, for instance, is the wearable market, smartwatches, where they need a very thin device. Okay. On the right-hand side, you have some of the key electrical characteristics that I have already covered. You have a picture here of the evaluation board that you may also order directly from us, or also through our different distributors. I think that's it. I just wanted to give you a quick overview of what we have and what we do. Thanks, Alex.
Thank you, Luc. As the last presentation, we will give the word to Andres. Andres is working at Miromico. He has joined Miromico in 2018, and he has over 10 years of experience with embedded systems, and he has worked for multiple research laboratories in Colombia, Italy, and Switzerland. He has also co-authored more than 20 papers, scientific articles, and is contributing to many open source projects. Andres holds a PhD degree in electrical engineering from the well-known ETH here in Zurich. Andres, please take over.
Thank you, Alex. And hello, everyone. My name is Andres. It is my pleasure to be with you here today to talk to you about the Internet of Batteryless Things. I'd like to begin by saying a few words about Miromico. So as a company, we were founded in 2002. We currently have over 40 employees based in the beautiful city of Zurich in Switzerland. And we are experts in low power sensing and networking, particularly for embedded systems. Here is a sample of some of our products. We can start with the smallest LoRa module here that can then be integrated into different types of products. So for example, a GPS tracker, an IoT button, and many different products that can then work alongside our LoRaWAN gateway. So this is some of the products that we currently have been offering for some time now, but today I want to talk to you about our new arrays of products in the energy harvesting domain. So to do this, I want to first talk about energy-driven design and what it means. So the first thing that you should know about energy harvesting is that there's a great power imbalance. So let me start by just drawing one axis of power, And you can see here that this is logarithmic, so I'm going over many orders of magnitude. And from the previous presentations, we've already seen that there are different types of transducers out there that can generate energy from the environment. And in the best case scenario, you can order them by the power density, which is how much power they can generate divided by the area. And the one with the highest power density is photovoltaics, which in the best case scenario can offer you at most a few milliwatts per squared centimeter. But most of the time, the power is going to be much lower than this. It's going to be highly variable, and at least for half a day, it will most likely be dark and closer to zero. Now, on the other side of the equation, we have an application which consumes a lot of power, and this depends a lot on the peripherals that we have and the applications that we're running. But if our devices have maybe a camera, they have a strong processing requirements, or they have a high power radio, this can easily go into the hundreds of milliwatts, or maybe even a milliwatt, depending on the type of communication schemes that you need. Now, luckily, we can design our devices to have a sleep state so that we can turn things off when we're not using them. And if you design your device properly, you might go into the microwatt range. So we leverage this sleep state and alternate between the active and sleep state to reduce our average power consumption to such a degree that it's equal to the power generated by a transducer. And this is the general idea of how you design an energy harvesting based system. But the first thing that you should understand about your environment is really how much energy it can offer you, because energy harvesting as a source is going to be sporadic. All right, it's not going to be a stable, steady source that offers you an easily predicted amount of energy. So to do this, it's really challenging. Here I have a picture of two former colleagues of mine, Moritz and Lucas, and we wanted to figure out how much energy we can get from thermoelectrical generators on a wearable application. And to do this, we needed to have large amounts of equipment. So you can see Lucas there on the right. He is carrying this big backpack with a car battery and an AC inverter so that he can power these powerful benchtop environments that have a very high accuracy. It's only with this two-person setup that we're actually do measurements out of the field, walk around through a normal use case of a wearable application, and really measure how much energy we can harvest. But this setup is quite complicated and cumbersome. So to do this, back in my old research group at ETH Zurich, we designed the Rocket Logger to facilitate these types of energy measurements out in the field. And one of the key features of the Rocket Logger is that we're able to do current measurements with very high accuracy. We can measure down to a few nanoamps with a high precision, and we even have two current channels to measure both the input current and the output current of an embedded system. So this Rocket Logger project is an open source project. You can go to this website, look at all the code, schematics, hardware files, and use it yourself. So this was a very successful project. It won an award in 2018. And this is a picture of how it looks like. So as you can see, in comparison to the previous picture where you have big, bulky equipment, it's really just a small device that you can put on your arm, and you can hook it up to not just wearable devices, but in general, any type of energy harvesting based embedded system. So this is currently being sold by Miromico, and it's actually being used by different researcher groups all over the world. Now, once we have this tool, we can really focus on this question of how much energy is available indoors. So to do this, to answer this question, what we did was we started a measurement campaign at ETH. We started a couple of years ago, and we designed this hardware that used the Rocket Logger. So that you see on the left and on the right, we have this device that is really just about being able to measure accurately the input power from a standard sort of solar cell. And we recorded not just the electrical signals, but also the environmental signals like the temperature, humidity, illuminance as well. So this is the floor plan of the offices, and at our research group, we had 6 different measurement stations, and I just want to go through some of the measurements that we have here. So this is station 14. It's relatively close to a window. It's facing east. And in this plot, what you see is the y-axis is the average input power for 1 hour. And in the x-axis, you see the hour of the day. So here 12, it means noon. So 6 is 6 a.m. And you can see that because it's facing east and is close to a window, you see this huge peak in the morning hours. In the best case scenario, we were able to harvest around 6 milliwatts, which is quite good. But as you can see from the color blue, it's not very often that we are able to record this. So most of the time, in red, we have very low energies. Now in station 17, which is facing west, we see a big peak in the evening hours. And in particular, you can see that because it's facing actually northwest, it's not entirely facing the sun, the peak is a little bit lower. It's around 1 milliwatt compared to 8 before. So one last measurement here, our station number 6. It was my former office, and you can see that there's a little bit of a weird outlier here close to midnight. And that's actually when I was writing my dissertation. So you can see this little outlier here. Now, I just want to point out that there is a difference in the power level because there is no natural light in this position. It was not close to the window. You can see that the top, it's around 100 microwatts, and you don't see a peak either in the morning or in the evening because there is no direct natural light. Now, just to give you a summary now of the energies, right? Before we were looking at the input power on an hour by hour basis. But when you look at the actual energy gathered throughout a day, this is the summary of those 3 offices. So this is a violin plot, and what we see here is just on the x-axis the energy, and the blue shades of the shaded area, it just shows the distribution. So the higher the peak, the more representative those measurements are. So in my old office, let's say the most energy that I was able to harvest was around, let's say, a few joules, 3 joules. In the one facing east, you can see that the maximum energy that we were able to harvest was quite large. It was 80 joules, but for the most part, we're in the a few joules, tens of joules domain. So in general, this is quite a bit of energy for embedded systems, and you'll get a feeling of this, of how much we can do with this energy budget a little bit later. All right, so now that we have a general understanding of how much energy we have available in indoor environments, I want to go into one of the applications that we're quite excited about here at Miromico, which is batteryless beaconing. Now, before you're able to use that energy that is available in the environment, you need to define an atomic step at the application level. And what this means, it's just a step that once you start, you cannot interrupt, and you're sure that you're able to finish it. And for our batteryless application, then we decided to just focus on BLE advertisements. So we built this sensor. We chose BLE advertisements because it's something that interfaces easily with the world. There are billions of devices that are compatible with BLE, like smartphones. Your computer most likely is able to receive BLE beacons as well. And so we built this platform. And just to give you an idea of, of the energy consumption from this platform, it looks somewhat like this. So on this power trace, the x-axis is in milliseconds, because this is quite fast to be able to read a sensor. So here in green, you see that when we're reading the sensor, we're consuming around 10 milliwatts. And when we're sending BLE beacons, it can go up to 40 milliwatts. And this is, again, an example of a low power application. So once we have this power trace and we calculate the energy consumed by this, what we see is that the distribution is actually rather narrow. So there is very little variability. When we do thousands of measurements, this is what the distribution looks like. They're always centered around 108.2 microjoules. Now, because it's so narrow, when we take the cumulative density function, it basically just looks like a step function. And this is key to what we define as the limit of batteryless storage. So if you find yourself within this, this point where the cumulative density function reaches 1, this is what we define as the maximum allowed energy storage for a batteryless device. So in this particular case, for this system, the maximum storage that we can have for a batteryless system is 109 microjoules, because this is where we would be able to guarantee that all of the tasks for this device are guaranteed to be executed. And when we choose this energy storage value, we can make two guarantees. We can guarantee that the device operates reliably, but we can also guarantee that it has the minimum startup time. And this is because we're using the smallest energy storage required. You can think of any storage that is higher and it will work, it will guarantee my atomic task, but it will take longer to charge just because the capacity is bigger. Now, just to tie this to the energy measurements that we saw earlier, in indoor environments, so even in my former office that was relatively, or that didn't offer as much energy as the others, we can see that this application will execute quite a lot. In particular, we can have an execution rate of around 3 packets per second for 8 hours during the normal workday, or at midnight when I was writing my dissertation. You can have lots of activations because there's a lot of energy available. But to be able to use this energy, so we still miss something in the middle. We saw the environmental energy and we just saw the application energy, but we need something in the middle so that these two can actually be connected reliably. And this is what we call the energy management unit. So this is just one possible solution to this problem of joining the application to the environmental energy. But this particular solution has some interesting properties. So the first one is decoupling, that we're able to do things independently. And what this means is that on the input side of things, we are able to guarantee that we can do maximum power point tracking. So in this particular case, we can take something like the ePiece chip here as a boost converter, and we can guarantee that regardless of the transducer, whether it's TG or solar panel, we can always follow the maximum power point, which depends on the voltage and the current. And because we do this independently, then we're able to guarantee that the energy flow into a capacitor is maximized. Now, on the application side of things, when we connect this capacitor with a down converter to an application circuit, we're also able to guarantee that we consume the least amount of energy for our application. We can even include some complex feedback control mechanisms so that we can minimize the energy consumption of this application and do things like DVFS to really minimize the energy. Now, the key aspect is that we do need to optimize this capacitor. We need to make sure that our capacity is as small as possible, but it can still guarantee the atomic execution that we mentioned in the previous slide. Now, to give you a very precise example of the advantages of this type of architecture, if we're in an indoor scenario where there's relatively little light, but we can still harvest 50 microwatts at 1 volt, we're able to do this optimally as an input, as the input energy. And on the output energy, we're able to guarantee that our application, if it needs 100 milliwatts at 2.8 volts, we can supply this. And we're not breaking any laws here, because it's all based on conservation of energy, because the energy consumed by our application is safely stored in this optimized capacitor before we actually consume it. So EMU-based systems have a very wide operating range. As long as our environment is able to provide at least 3 microwatts, we know that we're able to establish a flow of energy between the transducer and the application. And we could do so with a relatively high energy efficiency as well. The energy efficiency depends on many parameters, like the operating voltages of the transducer and the application. But we have been able to do measurements where we have actually recorded an energy efficiency of over 90%, which is very nice, considering that we do have 2 converters in this architecture. But overall, throughout this entire operating range, we can guarantee that there is reliable execution and minimized energy consumption on the application side, which is what gives an EMU a very linear relationship between the execution rate and the input power. We'll see this in action when we do the demo a little bit later. Now that we have seen the different building blocks of energy-driven design, we know that we can have these this sporadic source from an energy harvester. We really only need a small capacitor to be able to turn on our application circuit in atomic steps, and we can guarantee that our application actually executes. And the advantages of this is that batteryless systems are less expensive, they need less components to work, but they do have this limitation that when there is no input energy, they simply don't work. And this means that in the end, on the information side of things, we cannot guarantee periodic sensing. Luckily, there are applications where there is a correlation between the availability of energy and information, and we'll see some examples of this later. But overall, what I want you to take as the key message of energy-driven design is that it works whenever the environment gives it energy and it consumes it instantaneously to run its application, and does so with the minimum startup time. So because we optimize this capacitor, really, as soon as it receives energy, it wakes up immediately from 0 volts and starts executing. To view potential applications of energy-driven design, I would now like to give a brief overview of the beaconing ecosystem. So this works when a customer of a store walks in with his smartphone and there's the store's app, and as soon as he walks in, he's able to interact with the store with different ways. So he can access coarse localization services to maybe locate where a product is in the store. It can help with customer registration. So as soon as the person walks in, if the store has some orders that the customer can pick up, if it can be prepared immediately. It can also be used for payment services directly from the communication between the store's infrastructure and the application. Now, with these types of applications in mind, we've developed the batteryless MiroCard. Now, it's a small device, as you can see here. It's less than 5 by 4 centimeters. It's extremely thin, less than 2 millimeters, and it has been developed by Miromico in close collaboration with Epishine and EPs. So you can see that we use one of the Epishine solar cells, and you can't see it, but we also have the EPs chip with its fabulous cold start performance to power up the MiroCard as soon as there's some light. There are many features that we're excited about, not only the size, which is smaller than a credit card, but it's also immune to RF skimming. If you don't know what this is, the RFID cards that you currently have in your wallet, they're susceptible to an attack when someone stands up to tens of meters away using a powerful transmitter. They can remotely read the data inside your RFID cards unless you you cover them with special materials. With the MiroCard, you don't have this problem because as soon as you have this card inside your pocket, the solar panel is completely dark, and there's absolutely no way where you can shine light remotely and remotely power your MiroCard. So it's extremely safe from this perspective, but it's also quite powerful. We have a powerful Cortex-M4 processor in there. We have different sensors, and we can communicate using BLE to billions of standard devices already out in the field. And we can also implement specialized protocols. Now, applications for this MiroCard are many. The beaconing applications that I mentioned in the previous slide, all of those apply, except that you don't need a smartphone now. With the MiroCard, you can immediately start interacting with the store's infrastructure using just this small card-sized device. It can also be used for secure access control because we can use protected communication with things like digital key locks. We can also use this for asset tracking. So imagine the MiroCard as a sticker practically that you can paste on or put on top of devices. And as long as there's a little bit of light, so if they're indoors, you can rest assured that during the normal work hours, they will be periodically transmitting their position, and you can track their location throughout the day. But we could also use this for more traditional ambient monitoring and many other applications. The MiroCard will be released as open source and open hardware. It will have a permissive license, so anyone, researchers, companies, can use the source code to make their changes to address their specific needs. And we do this to try to build a community so that different stakeholders can interact, they can propose changes, and we hope that they can tailor this new platform to fit their specific needs. And we're very excited about the many different possibilities that batteryless devices like these can open up. So now I want to show you a demo of the different devices that I've talked about here. The rocket logger, a batteryless sensor, and I'll also give a quick demo of the MiroCards. So the first demo will be using the rocket logger to measure the energy input of a small batteryless device, and we can also measure the power consumption, and we'll be able to see this linearity between the input energy and the energy consumed. So the application for the first demo is just an ambient sensing, and we have an Android cell phone where we'll be able to visualize the measurements. Now, to summarize, just again, the rocket logger, it has many interesting features, and what we're really proud of is the seamless range switching that gives us a very, very high dynamic range from just a few nanoamps to up to 500 milliamps. Okay, so here's our demo. I'm recording this a little bit past noon at Miromico offices here in Zurich, and here is in this window we see a video feed of our setup. In the middle, I have a cell phone which I'm using just to record the luminosity of the room. I am a few meters away from the window, so I have a mixture of artificial light and natural light. And we can see that right now we're recording around 180 lux. On the left-hand side, we see the batteryless sensor with a solar panel and some cables that are being hooked up to the rocket logger so that we can visualize our voltage and current measurements. Now I'm going to turn to the rocket logger website where I can see all of my measurements. So currently the timescale is 1 second per division. So here this is updating every second with our measurement. In this graph, I see the voltage, and V1 is the channel that measures the solar panel voltage. And we can see that we're roughly around 2.5 volts on average. Here in the bottom, we see the current, which is negative because it's connected negatively. And we see that for the most part, we're harvesting almost 200 microwatts. And when it goes to 0, this is when maximum power point tracking is sampling the voltage of the solar cell so that it can adapt its impedance. So 200 microamps at 2.5 volts, that gives us over 400 microwatts of input power. So now I'm going to disable this measurement and I'm going to enable both measurements so that we see a bit better the scale. In this voltage 2, what I'm recording is the capacitor voltage. So this is an optimized capacitor. It's 100 microfarads. And you can see that it's charging up. It charges up rather quickly. When we reach this maximum voltage here, we activate our load. And this is when you see the voltage coming down. You can see that right now, even though the luminosity is quite low, it's 200 lux roughly, we still see multiple activations per second. Now, just to give you an idea here of the current of the device, when you see these peaks, these positive peaks, it's because the load is activating. So we can also measure the current of the load simultaneously. So here on the right-hand side, I have an Android device, and I'm going to open our MiroReader device application, and here is where I'm able to read all the measurements from our different devices. So at this point in time, I just have this one sensor, and I can see here it's in the meeting room, and I'm able to read the measurements. And you can see that this activates almost every second. There's a little bit of lag in the software, and it shows just the last packet received. But we see that it is summer, so the temperature is a little bit high. It's 26 degrees, relative humidity of 55%. So now I'm going to go back to the camera, and I'm going to show you the dynamic aspects of this batteryless system. So I'm going to turn on a different lamp, where you can see that the luminosity jumps up to almost 1,000 lux, more than 1,000 lux. And you can see here that the amount of activations increases significantly. So you see there are many more peaks than before. If I turn off the light, the luminosity goes down and the rate goes down with it. In the most extreme example, I am now going to cover the device. And when I'm covering the device, it's not receiving any input power, naturally. And you can see that it's slowly starting to discharge because there's 0 input power, and the device is still on, and it's consuming a little bit of power. At some point, this will discharge and go back to 0, but as soon as it's exposed to a little bit of light, after a couple of seconds, it recovers, and it starts to do measurements again. And you can see that the execution rate is still a little bit low because it takes a few seconds for the maximum power tracking to detect this new state. And now you can see that it automatically adjusts its impedance and increases its input power to the optimal point. Okay, so now I want to show you the Miro tag. So here I have 2 Miro tags. You can see that they're quite thin cards, and on this side I have the electronics. So you can see the microcontroller, different harvesting chips. This is the integrated antenna, and what I want to show you is that as soon as I turn it around, it will take a few seconds for this to energize, and once this energizes and sends its beacon, my Android device can recognize it. This card I have tied to my account, so this is why you can see here my picture, and it recognizes who I am. Just as an example, I'm now going to turn on this second device, and you can see that after a few seconds, it will then start emitting beacon, and it recognizes that this was Kevin's MiroCard. This is a colleague of mine who works here. And so you can see that it will behave just as the batteryless sensor in the left. When there's more light, it will emit more beacons, and this is why you see the order of the advertisements here change, because they continuously update. Okay, so this is the demo that I wanted to show you. Thank you again for your attention. for your time. Alex, I am now ready for the questions. Thank you.
Thank you, Andres, for your presentation. Now we have some time for Q&A. We already received a few questions. I will try to address all those questions with the different presenters. So let's start with the first one, which is probably to Luc. There is a question about, does the EP's MCU family have built-in Wi-Fi or cellular coprocessor or any modules that include them?
So maybe let me just switch on the camera maybe so that people can see me. No, unfortunately, they don't. Our MCU family does not have built-in the radio chip or the Wi-Fi. So this will be separate. However, at some point we are thinking of doing maybe a system in package or a module which will integrate the MCU plus a radio chip plus the AM chip. Next question, please.
Okay, thank you. There is a question from Antoine. I think it already has been answered during your presentation, but just to emphasize, are your boards or kit available for purchase, and where should people start with if they want to get their hands on energy harvesting solution from EPs?
So yes, the evaluation kits are available for purchasing. You can find a list of distributors on our website. If you go to our homepage, and on the top right, you'll see how to order. And then, depending on your region, you can select a local distributor.
Thank you. So your contact will also be included in the slides we will share after the presentation, so people can freely contact you after that. The next question is also to you, Luc. Could I use energy harvesting solution in a product such as a wristband with electronics inside?
Actually, yes, it's a huge potential for us, a huge market. We are talking to some big players. Unfortunately, I cannot give you any names, but they are developing fit bands, wristbands on top of smartwatches. Those ones are using actually the photovoltaic as an energy source. But yes, this is it's a key application for us.
Another question to you, Luc. The application using energy harvesting modules look very exciting. How optimistic are you for mass adoption of the technology, and how close do you think we are to see energy harvesting modules in everyday life?
At the moment, we see a trend with a strong growth in the adoption of energy harvesting, focusing first on the photovoltaic. You'll see more and more IoT devices on the market, and people will get bored of changing the batteries. And so we think that energy harvesting is the key thing, especially also with the environmental constraints. You don't want to bother with recycling the batteries and so forth. We are in production, in high volume production, delivering hundreds of thousands of units already, and it's only the start of a journey. Next question, please.
Going back to the wristbands we had in the earlier question, will they use supercapacitors?
So some of the customers are using supercap because of a small form factor. And this is the main reason, especially for the thickness. Okay, some others are using rechargeable batteries, but at a much less extent. So it's mostly using supercap. Next
okay,
question.
There is one last question to you, Luc. Where can we buy your chip in small quantities shipping to Switzerland?
Again, if you look at the website, we have a few distributors for the DACH region, Germany, Austria, Switzerland, like Tech Module, like Kamaka, for instance. And you may also order chips from Fujitsu, which is a worldwide distributor. So you'll have all the links on our website, or don't hesitate also to drop me an email if you cannot find this. We can deliver from, let's say, 5 samples, 10, 20 samples. So there's no real minimum order of quantity. Of course, I would prefer if you order 10,000 or 100,000. Next question.
Next question is for Andres. Just out of curiosity, does Miromico have the card as an open hardware and software project? Andres?
Can you hear me?
Can you switch to?
Okay, I think I'm able to unmute. Okay, so this is a very interesting question about open source and open hardware in particular. I'm talking from my experience, also from the Rocket Logger. This was something that was initially developed in research, and in particular at a public university. So let's say it originated from public funds, and as a researcher, the idea was to be able to produce knowledge that is used by the general public, by everyone, because we believe this fosters innovation, and it can allow different use cases to multiply, and for different people to look at a device and make improvements. Right. This is also part of the history of Linux and different software projects as well. So the idea with the open sourcing of this MiroCard is to also be able to open up and possibly start a community where different people can look at the technology. In the end, we want to be able to get energy harvesting out there in a bigger scale, and in the end, this helps the planet, and it's able to make a difference, hopefully, in the future. So that's the purpose. Maybe if I can ask a question to Luc. So you mentioned, Luc, that part of the mission at EPs is to harvest more energy and to consume less energy. So I get this from the processing side of things. Digital electronics, we can still try to optimize. What is your view on things like wireless communication? Do you think in wireless communication, something like BLE, we'll still be able to push down the power consumption and the energy consumption even further? Luc, we should look at your audio. I think you're muted.
Yes, I'm muted now.
Okay.
Are you looking at using BLE as an energy source, for instance, at 2.4 gigahertz or 2.45 gigahertz?
No, I'm just talking about consuming less energy with wireless. So do you think we're still able to optimize wireless communication and RF in general so that we can do more with less?
Yes, in fact, there is a BLE 5.2 standard coming up by reducing also the power consumption. So yes, I do believe that BLE, but not only BLE, like a ZigBee, a similar type of technology, could be also a good trend in terms of reducing the power consumption. And also, it's linked also to the CMOS technology which is being used. You know, nowadays the most advanced radio chips are using technologies like 14 nanometers, 28 nanometers. We are talking now about 5 nanometers, which will lead to a further power consumption reduction.
All right, thank you.
Okay, one more question for you, Luc. How efficient in terms of power conversion is the cold start mode relative to the normal mode? And in my experience with Texas Instruments BC family chip, the cold start was orders of magnitude less efficient than normal mode, many hundreds of times slower to cold start versus charge the cap via a diode. So what is your opinion on that? Or
I'm not sure I fully understand the question in terms of efficiency of cold start. What we see so far, let's say, I cannot comment about the TI chip, how they can achieve, but what we see so far is an efficiency of between 90 and 95% of efficiency of what we see. Okay, this is on the photovoltaic. If you look at the RF, this is much more challenging. Basically, you can have a drop of almost 1,000 times between the energy you get from the RF, the antenna, for instance, and the one you want to use, mostly because of the loss in the air and also the limitation of the distance. The longer the distance is, the less energy you can extract from the antenna. Okay. Next.
Thank you, Luc. Next question is for Andres. What part of the hardware design forces the low limit of pin to 3 microwatts? What would be needed to go lower, for example, into the 100 nanoampere range?
Okay, so sorry for the delay. The 3 microwatts is a reference to the ePiece chip. So the MiroCard uses the ePiece chip, which, as Luc mentioned, one of the key features is the cold start circuit. So I also have plenty of experience with the BQ family, and I have, just from my experience, it was also through this diode that was charging up the capacitor, so it was very inefficient. But with ePiece, I think it's part of their IP, how they designed their cold start module so that you're able to have very fast startup. And so from my perspective as a user of the ePiece chip in the MiroTag, I can just easily claim they're 3 microwatts. Now, if we want to go below that, oh, sorry, and just also to clarify, I have also tested it. We could also go down to very low microwatts, and it actually does boot up. So this was something that I was personally very happy with. But to go below that, then you basically just need custom chips. So I know, for example, of a company called Wiliot. It's an Israeli company, and they do their own ASIC design, and they have a very small chip that can harvest RF, and they have a custom processor, and they're in this nanoamp range. So they can harvest RF, and they're able to do very small computation and send packets with very low power levels. But they're able to do this in the nanowatt range because of their custom silicon. So this is for chip designers to really exploit nanoamps. There are also microsystems. So I know there are different research groups all over the world working on miniaturized systems that work with nanowatts. Now, next question.
There are no more questions. Okay. So I would take the chance to thank you everyone for paying attention and joining our webinar. As mentioned in the beginning, we will publish all the information, all the slides on our website. We will send out a short email in the coming day asking you to fill out a survey to get some feedback on our webinar and to see what we could improve for the upcoming seasons. And I would like to take the chance to already also thank you for the interest, and we will be happy to get in touch and talk to more about all the topics and sharing information with you. So have a good day, everyone, and good night.
Thanks, everyone, and thanks for organizing this event. Thank you.
Thank you.
Thank you, everyone. Bye.
Bye.